see if it actually fixed the one I've already made. It does. So in room 1,
Yes.
I believe I've already assigned everyone. So I think if you click on room 1, you should be able to just, you know what, I'm going to be here. I'll do it. That's probably easier if we do that.
I can. I mean, yeah, you could, but I could also do it because if you don't need to stay till the end potentially, unless you want to.
I am going to.
All right. Okay,
so we'll just do it that way then. That's fine. All right. So basically, I just want to make a quick statement that unfortunately, 2 of our examiners were not able to make it. Thankfully, the University of Ottawa regulations specify that provided that more than half of the jury is present, that we can go ahead and have met quorum. So in this instance, we have Professor Shahata, Professor Edeker, and Professor Martin Perez. That's 3 out of 5. So we have in fact met quorum. Diego, thank you for testing your presentation earlier. Basically, at this time, what's going to happen is everyone who is not a jury member is going to be asked to leave the room. So that's all of our guests present here, as well as Diego. Please make your way into the hallway. We'll let you know once it's time. While I do that, I will move everybody here into a breakout room.
All right.
Thank you, everyone. So basically, Professor Lethbridge.
I actually don't know who the external examiner is.
Okay, so the official external examiner is Professor Jim Edeker. We have a special invited examiner who's Professor Medhat Shahata from Ryerson. I believe Professor Edeker is from University of Portland.
No, it's Oregon State.
Oregon State, sorry about that. It's okay.
So Jason.
Hi, Jason.
Okay, so Jason is here. Okay.
Yeah, we just got to wait a couple more minutes for a few more people to jump into the breakout room.
So Jason Edeker is the external examiner. I'm just trying to make sure this, because I got the list here. I'm going to admit the. Oh, okay. There's another person outside who's going to admit as well. Okay, very good in the waiting room. Okay, so before you start, I just wanted to just mention a couple of things about the process.
All right.
First of all, I was asked by one of the examiners to point out to you that when he's asking questions, you may not be able to see him in the eyes because he may be looking at a different screen. So just be confident that he's still there and still looking at you. Okay. The second thing is I'm addressing this to the audience, and that is to avoid disrupting the process. Please, no talking, but in particular, please don't leave. I'll give you the opportunity to leave after this presentation, but during the presentation, please stay where you are, and also during the questioning, please also don't leave at that point, because the opening and closing the door could be distracting to the candidates. It's a stressful time. All right. Sure. I might also give you a chance to leave between the end of the first round and the beginning of the second round in case you're not bathroom break, but then you can't come back in after that. All right. That's just a question of procedure. And we are allowed to take masks off if you're 2 meters, 6 feet from somebody else. You're close. You'll have to leave your mask on unless you want to move to another seat that's somewhere further away. Okay. So you can keep your mask off throughout the process and so on. All right. So we're going to start off the two external examiners and the internal examiner and for a first round after your presentation, and then we'll have a second round where people can jump in a little bit. I've been told that your presentation is about 28 minutes, so I need to be reasonably strict because that's quite long. You'll see me signal you at 30 minutes to say you got to stop now. Okay.
All right. Mm-hmm.
All right.
All right. Sure.
Okay. So take it away and good luck.
All right. Thank you. All right. Okay. Just let me start. All right. Good afternoon, everyone. My name is Diego de Souza. I'm a PhD candidate at the University of Ottawa under the supervision of Dr. Leandro Sanchez. I would like to thank you for having me here today. It's such a great honor to be presenting my thesis, Avoiding and Mitigating Alkali-aggregate Reaction in Concrete Structures to you.
Sorry, Diego. You're actually not sharing your screen.
Oh, really?
Yeah, I'll do that if you don't mind.
Okay, sorry.
It's okay.
Oh, yes, I should have seen on my screen that you weren't sharing it. Yes.
Hopefully that time is not counting, right?
No.
All right.
I don't worry about that.
All right, but I already presented one slide. So it's okay.
So
Yeah. Pegadinha do malandro.
I was just assuming that whatever was on up here was shared. So.
All right.
Yes.
So now.
Okay, now I can see it here too. Oh, very good.
All right. So let's start again.
Yes.
Okay. So good afternoon, everyone. My name is Diego de Souza. I'm a PhD candidate at the University of Ottawa under the supervision of Dr. Leandro Sanchez. And I would like to thank you for having me here today. It's such a great honor to be presenting my thesis, Avoiding and Mitigating Alkali-aggregate Reaction in Concrete Structures to you. So what is AAR? AAR is one of the most harmful distress mechanisms affecting the durability of concrete worldwide. Its development can cause internal cracking, affecting the mechanical properties of the concrete and decreasing its lifespan. AAR can be divided in two main reaction types: alkali carbonate reaction and alkali silica reaction, which is the most common and the one that I will be exploring more during this presentation. So for the occurrence of ASR, three elements are simultaneously necessary for the occurrence of the reaction: the presence of reactive aggregates, high moisture condition, and high alkali content. Without one of these three elements, the development of the reaction, it's not possible. And once it starts in the field, there's no universal solution that could be applied in different scenarios to mitigate the reaction, for the reaction. So the thing here is that we should act to prevent the reaction to happen. So what we can do to prevent the development of ASR in the field. So one of the ways is through the use of chemical admixtures. For example, lithium nitrate, which can change the dissolution and solubility of reactive silica, forming a protective barrier surrounding the aggregates and changing the chemical composition of the ASR gel. The problem is that these products are too expensive and their effectiveness is constantly questioned in the literature. Another way is through the use of supplementary cementing materials, which are byproducts for different industries. and these materials can be used in combination with cement to enhance the hardness properties of the concrete. For example, here in Canada, we have a performance-based design standards that give us engineers good practice to identify the degree of alkali reactivity of aggregates and measures to avoid deleterious expansion in concrete. For that, it's necessary to know the reactivity of the aggregates and the level of risk of ASR development. With those information, we can then select the best level of prevention, which is basically this table here that give us minimum amount of cement replacement by the most common types of SCMs used in Canada. However, new evidence in the literature indicates that SCMs only delay the occurrence of ASR in concrete. So we ask ourselves, do SCMs avoid or delay mitigate ASR-induced expansion in concrete? And if SCMs only delay the process, if it's possible to find another products that would act as a backup to mitigate the process, the ASR development. So going through the literature with those questions in mind, we then found that among the different alternatives, the self-healing technology might be the best option because this type of materials can enhance the self-healing of the concrete and change the damage within the concrete. So what is self-healing of concrete? It can be divided in natural healing process that can be caused by calcium carbonate formation, continuous hydration of the unhydrated binary grains. It's important to mention here that SCMs can enhance this behavior. Also, it can be caused by cement matrix swelling and sedimentation of solids within the cracks. And the overall behavior of the healing ability of the concrete can be enhanced by the use of artificial healing agents, such as microencapsulated bacteria and crystalline admixtures. So we ask ourselves then, are self-healing process able to change ASR development? And if we use artificial healing process, these materials can work as a supplementary action to mitigate further development of ASR in concrete. With those questions in mind, we then developed the structure of this thesis, of this research, in which first we would like to combine this self-healing technology with SCMs to develop to mitigate the further development of ASR in concrete. However, we would also not only to use these materials for new concrete, but also to use in aging concrete materials. For example, here, if we have a situation once we already have the development of ASR, can we use this technology to further mitigate the reaction? And at the end of this research, we would like to propose a framework for an optimized selection of raw materials to prevent ASR in concrete. In other words, we would like to go from a descriptive selection of raw materials to a performance-based selection of materials. Also, I would like to mention that we developed two parallel research here to first understand autogenous and autonomous self-healing of concrete, and then the influence of high volume of SCMs on ASR distress development. We used two different reactive aggregates, a gray walk reactive coarse and a natural fine reactive aggregate. The overall concrete mix design are based on the most used standards in North America. And it's important to mention here that the volume of reactive aggregate is always constant for all mixtures. So what were we measuring here? First, we are going to be measuring the induced expansion over time of the concrete specimens, but also the induced damage due to ASR. And here, damage, it's defined as the mechanical properties reduction, in which we'll be measuring through compressive and shear strength. Also, the stiffness reduction, which is assessed by the modulus of elasticity, and the physical integrity and durability reductions, with the internal cracking extent of the concrete through the techniques of stiffness damage test and damage rating index, which I will be explaining next. So SDT, it's a great tool in which we can quantify the distress degree in concrete. And besides the modulus of elasticity as an outcome, it also gives the stiffness damage index, which is the ratio of the dissipated energy to the total energy applied to the system, but also it gives the plastic deformation index, which is the plastic deformation to the total deformation implemented into the system. As a microscopic evaluation, we use the damage rating index, in which we count the total amount and the different types of cracks per centimeter square of a polished surface of concrete. And with this technique, we can have the extent of damage in concrete. For example, here we have different features for cracks, and for each of them, we have a weighting factor to give a different importance for the cracks, and which is based on the development of damage in concrete. So in the first objective of this research, we are going to be casting different concrete cylinders with 2 different reactive aggregates, different binder materials, and different chemical admixtures. The chemical admixtures here are the self-healing agents. After casting, we're going to be subjecting the specimens to the development of ASR, and over time, we are going to be measuring them mechanically and microscopically. So here, just a general overview of the concrete mixtures we used. Once again, we follow the mix design. It's based on CSA 27A. We used 4 different types of SCMs, slag, fly ash, silica film, and metakaolin, and their amount, it's based on the table from CSA. However, instead of using the higher amount here to avoid the development of ASR in concrete, between the 2 years of evaluation, we used a little bit less to have a delay in the development of ASR. However, we are looking to have some development. Why? Because here we would like to then combine the different SCMs with crystalline admixtures to see how they would behave together. We use 4 different types of crystalline admixtures. Also, we mix them differently to try to enhance their behavior of healing. And also at the end here, as I mentioned, we combine crystalline admixtures with SCMs. The results shows that all mixtures we produce in the lab were able to first mitigate, change ASR kinetics, decelerating the reaction rate, but also decreasing the final expansion after 2 years of evaluation. As we can see here, for both aggregates, and as we can see here, the overall results can be split in 2 main groups. In the first one here in the top, it's basically the concrete specimens in which we only add the different crystalline admixtures in the concrete. And in the bottom here, we have both SCMs made concrete and SCMs made concrete with crystalline admixtures. As we can see, all concrete mixtures were able to change ASR kinetics and expansion development. So now let's see how they behave regarding the distress development. As we can see, through the stiffness damage index, in which we can have a good view of the internal damage of the concrete, we can see clearly that adding crystalline admixtures in the concrete, we were able to decrease SDI number for equivalent expansion amplitude, which means that the number of crack and the internal damage of the concrete, it's reduced. So to try to understand this behavior, we then test the specimens for a mechanical property that it's aggregate dependent. And as we can see, for comparable expansion amplitudes, doesn't matter our concrete mixtures, which one we are using. If we are using crystalline admixtures, SCMs, doesn't matter. The thing here is that the modulus of elasticity loss, it's the same for all concrete mixtures for comparable expansion amplitudes. And this can be proved by the fact that once we count the amount of cracks within the aggregates for the different concrete mixtures, we can also see that for comparable expansion, the amount of cracks is also the same. So why did we have such difference in SDI value, for example? Why did we have a decrease in the internal damage? To evaluate that, we then check mechanical properties that are sandwich-based dependent. And as we can see here, using crystalline mixtures or mixing them with SCMs, we can see a clear sign that for a comparable expansion amplitude, they can reduce the compressive strength loss. But also we can see that once we use only SCMs in concrete, we also had such decrease in compressive strength loss. So why did we have that? We are not using crystalline admixtures here. So to explain all this behavior, let's stop a little bit and let's use the results from the parallel research we made. First, understanding the ability of concrete to self-heal, we developed different concrete mixtures. After 28 days, we preload them up to 90% of the failure load. And then after preloading the specimens, we tested for DRI. As we can see, increasing the preloading level, we have an increase in the amount of cracks, especially in the cement paste as indicated here in this orange chart. After taking the DRI number and counting the amount of cracks in the cement paste, we sealed the polished surface of the concrete, and then we place them back on, in an environment to cure again for more 90 days. It's important to mention here that we did not use reactive aggregates for this analysis. After second curing of 90 days, we then test again for DRI to check the ability to self-heal of the concrete specimens. And as we can see, only by adding SCMs in the concrete were able to heal 50% of the cracks in the cement paste. This is a great value, and this proves that the self-healing of the concrete can be enhanced by the use of SCMs, as mentioned in the literature. However, if we use the crystalline admixtures, we can clearly see that the amount of cracks that were healed, the amount of cracks in the cement paste that were healed was approximately to 80%. So indeed, crystalline admixtures can enhance the ability of concrete to self-heal, and this explains the behavior that why did we have such lower compressive strength loss for ASR affected concrete. However, as we can see here, the combination of crystalline admixtures with SCMs decreased this ability to self-heal. So, but on the other hand, we have the higher decrease in the compressive strength loss was in the mixture in which we have SCMs and crystalline admixtures. So why did we have that? To try to explain this behavior, let's use the second parallel research, in which we evaluate the changes on ASR gel due to the high volume of SCMs. And we test the ASR gel in the cement paste, ITZ, and internally to the aggregate through a microindentation analysis, which give us the mechanical properties of the ASR gel. In this case, the surface hardness, translated here as Vickers hardness, as we can see, increasing the SCM's amount in the concrete, there's a significant decrease in the Vickers hardness for ASR gel in the cement paste or ITZ. However, within the aggregates, the average of the results are pretty much the same, indicating that SCMs does not have influence in the properties of the ASR gel within the aggregates. So to try to explain this behavior here in the cement paste, we then check the chemical composition of the ASR gel through the EDS analysis. And as we can see here, changing the ratio of calcium to silica in the ASR gel, there's almost a linear correlation with the Vickers hardness. In other words, if we use more SCMs, we will have a decrease in this ratio and then a decrease in the Vickers hardness as indicated here. And according to the literature, decreasing the amount of calcium in the ASR gel changes the swelling properties of the gel. Now, combining these results with the results and the ability to self-heal of the combination of crystalline admixtures and the SCMs, we then can explain why did we have such lower value for compressive strength reduction. And finally, for this objective one, we count the amount of cracks in the cement paste of the ASR affected concrete. And as we can see here, using crystalline admixtures or combining with SCMs or only SCMs alone in the concrete, we can clearly see that we have less cracks in the cement paste due to the ASR development. In other words, this proves that first, in enhancing the self-healing of concrete, we were able to change ASR kinetics, but important here is that we were also able to change ASR distress development. So now that we know that it works for new concrete, can we use this technology as a surface treatment of ASR affected concrete as a feasible solution to mitigate further reaction and ASR induced development in concrete? So for that, we cast different concrete cylinders with the same two reactive aggregates as before. but now only using Portland cement as a binder material. We subject them the specimens to develop ASR, and once they reach specific expansion amplitudes, we then treat the surface differently. After the treatments, we subject the specimens again to ASR development, and over time, we then evaluate mechanically and microscopically. So here is just a general overview of the different coating materials and different surface treatments we apply. I just would like to emphasize that we use crystalline surface waterproofing materials, which is the focus of this research, and we mix this material with different products such as fibers, high performance silanes, cementitious-based materials, lithium nitrate, water repellent, and nanosilica. As we can see with the results, doesn't matter the initial expansion development of the concrete before the application of the products. Once we treat the surface of the concrete specimens, we have a change and a decrease in the final and the expansion development of the concrete. The only exception here is the treatment in which we sprayed lithium on the surface of the concrete specimens that show similar behavior than the control specimens. I would like them here to compare the results from 0% of expansion once we apply the different treatments at this point with those in which we apply the different products at 0.30% of expansion. Why I would like to do that? Because as we can see, I would like you to save this information because it's important that the higher the initial damage of the concrete, it seems that the different surface treatment are more effective to reduce residual expansion in the concrete. This is a weird behavior, but I would like you to save this information because it's going to be important after. So also I would like you I would like to highlight that the treatment in which we combine crystalline admixtures with waterproofing on average is the one that shows the best behavior for expansion, but also the combination of crystalline admixtures with fibers also show one of the best behaviors on average. Evaluating the internal damage of the concrete. First, I would like to highlight again that all mixture surface treatments were able to change ASR expansion development, but once they reach specific expansion amplitudes, we can see that the internal damage for comparable expansion, it's pretty much the same among the different surface treatments. The only exception here is the combination of CA with fibers that show lower expansion development, but higher internal damage. At the end of this objective 2, we propose different charts in which we correlate the performance loss of the concrete specimens with the different surface treatments. I would like to emphasize here that the performance loss were calculated as the average of all mechanical properties evaluated in this research. So just zooming in here to explain the charts. In the bottom of the charts here, we have this black dashed line that represents the initial performance loss of the concrete before the application of the different surface treatments. And why did I ask you to save that information about the expansion? Because if we see here, applying the different surface treatments at 0.30% of expansion, after 1 year and 2 years of exposure, the overall performance loss between the different treatments are pretty much the same, even comparable with the control specimens. In other words, it indicates that the earlier we apply the different products, the better the results. Also, these results here emphasize the fact that comparing the results from 1 year to 2 years, it highlights that the maintenance is important to keep the performance loss of the concrete at lower levels. So we saw that we can change ASR development once we treat the surface of the concrete. However, with the results here and also with the data from the literature, it's evident that the prevention is the best solution. So at the end of this research, we would like to propose something to enhance the prevention against ASR. And for that, we propose a framework for an optimized selection of raw materials to avoid or mitigate ASR in concrete. In other words, we would like to go from a descriptive selection of the raw materials as in the CSA table to a performance-based selection of the raw materials. And for that, we use our analysis. Now, our analysis is based on the ternary plot of the main oxides found in the binder materials. And I plot here the chart with the most common types of binder materials located here based on their chemical composition. And the idea of putting this together is to show you that what we are looking for is to find different combinations of these materials in which we will have a chemical composition that will locate us in a safe region to prevent ASR in concrete. For that, we went back through the literature. We plot the results from the literature in this graph here, and we can see that following this yellow arrow here, we have a trend to prevent better the development of ASR in concrete. So with that information, we then select 9 different points in this plot to first try to map the behavior of this path of prevention against ASR, and then to understand better the influence of the main oxides in the prevention against ASR. Also, I would like to mention that it's such a great thing to have this point fixed because we can analyze them differently. For example, if we follow these blue arrows here, as indicated, we will have a constant amount of aluminum for each of them here. But if we follow their indication, we will have a decrease in the amount of calcium, increase in the amount of silica, and at the end, we will have a huge decrease in the final expansion of the concrete. But now, if we follow the fixing the silica amount here and following the arrows, we can see that decreasing the calcium, we have a decrease in the calcium amount and an increase in the amount of aluminum, and we also have a decrease in the final expansion, but not as clear as before once we fixed silica, indicating that the amount of silica in the binder materials seems to be more important to mitigate and to prevent the development of ASR. And now, if we evaluate differently again, but now fixing the amount of calcium, we can clearly see that decreasing the amount of aluminum and increasing the amount of silica, there is a decrease in the final expansion of the concrete, indicating that indeed the amount of silica in the composition of the binder materials are more important to prevent ASR in concrete. And then just to emphasize the fact that decreasing the amount of calcium and increasing both aluminum and silica, we have a huge decrease in the final expansion of the concrete. With these results, and also summing with the results from the literature, we were then able to propose a framework to mitigate ASR in concrete, in which we have different regions, and for each region here, it's based on the risk of the ASR development, as in the CSA 27A. And for example, if we have extremely high risk of ASR development, the composition, the mixture of our binder materials and the chemical composition of them together should be within this red zone here to prevent the development of ASR, or above this zone, and so on for the other mixtures, for the other risk of development. In conclusion, increasing the amount of SCMs, there's a decrease in ASR kinetics, also a decrease in the distress development for equivalent expansion, a decrease in the amount of cracks in the cement paste, but the amount of cracks in the aggregates are the same. This behavior can be explained by the fact that self-healing can recover mechanical properties of damaged concrete, and it was proved that self-healing of concrete were able to heal up to 85% of the cracks in the cement paste. Moreover, this proved that crystalline admixtures can indeed change ASR kinetics and distress development. Also, the mixture in which we combine SCMs with crystalline admixtures, we had the most effective mixtures against ASR development. And as I asked in the beginning of this presentation, if the self-healing could change further mitigation of ASR, it was proved that they can indeed provide further mitigation after ASR development. It starts on SCMs made concrete. And then finally, coating and sealers were able to modify ASR kinetics. However, once we use the crystalline admixtures as a surface treatment, this material were not able to heal internal cracks on ASR affected concrete. In other words, the internal damage, just follow closely the expansion amplitudes. And at the end, we were able to propose charts to help in the decision-making of engineers to first better select the materials, then the best timing to apply them. Also, the charts highlight the importance of maintenance. And at the end, we propose the framework to mitigate ASR, to help engineers in the decision-making, to better select the different binder materials and their combination, to have a prevention against ASR based on their performance. So thank you. I'll be pleased to answer your questions.
Excellent, thank you very much.
Thank you.
So we will move on, and if somebody wants to leave, they can. Other than that, we'll move on to the first external examiner, Dr. Jason Ideker, who will ask you questions.
Mr. Chair, should we change the mode so that...
It probably would be good if you could unshare your screen, so that you can be seen, although you might be asked to share your screen again and share something later on. Yeah, great.
Unshare?
Yeah, so you stop share, yeah, that's right. And so now, Dr. Ideker should be visible.
Yeah, he's here.
Right.
Yeah. Can you all hear me okay?
Yes.
Okay, great. Really nice presentation. Quick. This is definitely a difference from the US system. We have typically more about 30 to 45 minutes for a presentation. So it was interesting to hear that sometimes it's even faster at 15 minutes, but I certainly understand that reason to get to the point quickly. Yeah, I thought you did a nice job of pulling this together in the presentation. I have a number of questions for you. And I think from your presentation, a few things that I had question-wise when I was reading through the thesis are a little bit more clear now, so I think that's good. I guess to start off, just a very basic question on ASR. And can you just distinguish the difference between what makes ACR or alkali carbonate reaction different from alkali silica reaction?
Yes, overall for alkali carbonate reaction, in that case, we should have carbonate rocks that in which we have the dedolomitization of the dolomite in these rocks, and of course we have first. It has been proved in the literature that the mechanism of damage of these rocks are different. Normally we have cracks going more closely to the surface of the aggregates and then going through the cement paste. Different authors indicate that this reaction is a type of ASR in general, but considering the mechanism of damage of this of the ACR and this dedolomitization that we have in the dolomite minerals in the rock, I would say that this mainly is the difference between ACR and ASR.
Okay, great. What about mitigating or preventing ACR? Is there a way to do that? What are your thoughts on that?
Yeah, we are checking that. It's so far there's no mixtures or ways to really mitigate or prevent the occurrence of ACR in concrete. Once we have this type of rock, it's good to avoid the use of this type of rock because and this type of aggregates, because normally we don't have a good way to prevent its occurrence once we have all the conditions for its development. We are trying to find a way with this research as well. We are using ACR aggregates, but everything indicates so far, we did not add any results in the thesis, but everything indicates so far that even all these mixtures that we developed in the lab are not possible to mitigate ACR once we have the reactive aggregate.
So even with the possibility of looking at some self-healing agents, still not effective in the case of ACR?
It seems that it's possible to change the kinetics of the reaction, but in general, it still seems that at the end we will have such great development of the reaction that will have a damage in concrete. even using crystalline admixtures or combining them with SCMs. The results.
Okay, that's great. I think it's interesting that you've looked into that as well. So maybe just changing gears a bit into the work that you did. I think one thing that's really interesting is you used the two-key or tucky test. Some people say that differently. Why did you go with that particular statistical method? And did you look at others potentially, and why you chose?
Option to try to using the technique? It was first because I'm more familiarized with the technique, but also because we can compare average in parallel, like for both different mixtures. For example, if we use ANOVA, we will have like such a great variability in the data that it's kind of hard to really understand the impact of the different mixtures. We have like such a great like variation considering all mixtures, but once we have, for example, Tukey, we can compare them like in pairs, and then we can have a straight analysis between the averages, and then we can clearly see, at least like for me, it's clearer to see the impact of the different mixtures and the different variables that we apply in the different concrete mixtures.
Okay, yeah, I mean, I think that just as a community, ASR-wide, this is one of the things we tend to struggle a bit with. A lot of times because we're trying to test a lot of different combinations of materials and fairly different test methods or test environments. And so I think it was interesting that you've got that. You have some good justification for why you use that. I think that's going to be important for other people to look at and potentially consider that. So yeah, it's good to see your insight on that.
Yeah, can I just add one more thing?
Of course.
Yeah, one of the reasons as well, it's because, for example, if we compare, let's say that we are going to compare the influence on expansion. Once we have, for example, a variation in the final expansion that goes from almost 0% of expansion to 0.60% of expansion, if we compare all together, it will give us an answer that, yes, your mixtures are different, so you have like influence in the final expansion. But then it's good to evaluate them in pairs, because if we have like two different mixtures that have close values of expansion, we can see if indeed they are different or not. So this is something really good to see with this analysis.
Right.
Yeah.
So I think, toward the end of your presentation, I think it was maybe slide 35 or 36. I might have missed the exact number, and you don't need to bring it up. You can go look at it on your screen just to familiarize yourself. But you talked a lot about the importance of applying surface treatments, especially at the right time, right? Applying them early on sort of showed the most efficacy. But then you also said, well, even though we applied them at these discrete times, there was still a decent amount of damage internally from stiffness damage testing, from the DRI work that we did, and you still see fairly high levels of expansion that would probably be not desirable in structures. And then you sort of pivoted and said, so the best way is still to prevent ASR from happening, in the beginning. So I want to push you a little bit on it and hear from you if you months, or do you think that shouldn't be done at all and we really need to focus on prevention?
Yeah. First, for example, here in our analysis, we use like extremely highly reactive aggregates, and then it seems that the results, it's more a question of limiting water to diffuse into the concrete, and then decelerating the reaction rate with the use of the different surface treatments. So in one hand, I believe that if we have a case of ASR in the field, like that we already have the development of ASR in the field, the results here shows good evidence that we can do something to try to mitigate further expansion development and internal damage development. Once we can suppress the expansion of the concrete, we will have less internal damage. But once we have the development of expansion, the internal damage will follow closely the expansion. So in one hand, we can use those data to try to mitigate and retard even more the development of ASR in the field. But I would say that always, if you have a situation in which you know that you're going to be using reactive aggregates, the prevention is the best option. Indeed. Yeah.
Sort of, I mean, building on that a bit, you mentioned maintenance also, right? And sort of showing the importance or taking that importance about maintenance away from some of the figures you had. And I think you did a really excellent job of displaying that in your figures. But I think for the most part, but I may be wrong, you only did single treatments and then subjected the specimens back to the exposure environment. Is that correct? Or did you do some with multiple treatments over time?
You're right. I did not apply at different periods of time, but the evaluation, for example, at 1 year and 2 years showed that our specimens after treating, like over time, the performance loss keep increasing. So this indicates that if we have like these products applied on the surface, if we keep the maintenance of them, we might retard even more the performance loss of the concrete. It's more in this idea because we did not really apply like twice or 3 times the different products in the surface to try to see indeed the influence of the maintenance directly, I would say.
Yeah, I think that's just an important thing to keep in mind. I mean, certainly if we could get, you know, all the different agencies that are involved in maintenance of concrete infrastructure to even probably do 1 treatment, that might be a big win over what's happening sometimes, right? So I realize pushing for 2 or 3 treatments could really be even more of a challenge, but I think it's important to not lose sight of that for the future. So it's not a criticism of your work. I think you're very much in line with what we could even reasonably expect to happen. But I think it's an interesting thing that you may want to look into in the future, depending on the direction your career takes or other folks in the room who are listening and working on their, you know, PhDs or master's degrees, just to sort of think about that, you know, of coming back a few times and seeing how effective you can be, because we know slowing down ASR in the field or stopping it even is one of the probably the most challenging things we tried to do in the area, right? So it may take a more aggressive approach, especially in the case where you have extremely reactive aggregates like what you've got. So just more of some commentary, but good to hear your thoughts on it.
Yeah, it's also good to mention that this is like a first draw of these charts, and it would be also very good to test for different aggregates as well, because the outcome might be different as well. So it's something that we still need to keep developing for sure. You're more than right. Yeah.
So I have one final sort of, it's more of a comment for you, and then I'll pass it on to Dr. Shahada. But in the figure in your thesis, it's figure 10.2. It's one of the last figures that you showed today, maybe on slide 38 or 39, where you've got sort of the ternary plot, and then you have, you know, a really nice description showing where you need to sort of be on an oxide analysis basis for preventing ASR. One comment I have is that I think the way that figure is designed, it reads as misleading if someone looks at it on its own, because it looks like you have an extremely high risk of ASR in that red zone. And what you're actually trying to say is this is the area you need to be in from an oxide composition standpoint to address a concrete mixture that has an extremely high risk of developing ASR. And I think it even took me until your presentation today to understand that. So, you know, I'm not always the brightest person in the room, but you're going to have a lot of people looking at this potential framework. And I think it's one of the strong points of your dissertation. I would think about rebadging that in a way that as a practitioner looks at that for the first time, or someone who's not as familiar with, you know, the field of ASR and ASR research, that they get more out of it, that they need to be in that zone rather than avoiding that zone.
Yes, yes, this is a great comment. For sure, we will address in for the development of this Turner plot. And thanks a lot for your opinion on it. It's great to hear. We are still in developing this this framework. So yeah, for sure, we will take that into account. Definitely.
Great. Well, I will pass things on to Dr. Shahada, I believe, at this point.
Okay, thank you very much, Dr. Edeka. We'll move on, as said, to Dr. Shahada.
Thank you. So, Diego, very good presentation, and I did enjoy. I echo Dr. Edgar. I enjoyed the thesis as well as the presentation. What I like is really how you took a big comprehensive thesis, and in the presentation you tied the different components together. You have done a great job in that. So
thank you.
Just want to start by this. It's really you did a very good job presenting.
Thank you.
Work. Question. So I'm going to start with where Dr. Edgar left, which is the alkali carbonate reaction.
Mm-hmm.
In your thesis, you said that the micro hardness, you studied the micro hardness of the ACR product.
Yes.
Which product? Is it the dolomitization or?
Well, we tried the most to find a gel on it. Yeah. Of course, that with this analysis, as you mentioned, we were able to see some ASR gel within the aggregate that it's ACR aggregate that we used here, because in the gel that we evaluate, or let's say in the reaction product that we evaluate, it was clear that there's silica on it. Even in the chemical composition of the reaction product that we found within the reactive aggregate. So in one hand, which it's pretty clear, differentiating the chemical composition of the product within the ACR reactive particle with ASR one, it's clear that we have a higher amount of calcium in the chemical composition of the reaction product. And the values, it's not that far from the values that we found for example, ASR affected concrete that we found in the gel within the cement paste. So this is something that came to our head, that this is something that might be a difference in the different reaction products between the two different aggregates, for example. And this changes a lot the mechanical properties of the product within ACR gel.
But the ACR gel, Diego, even so, the fourth theory, the latest theory of ACR by Katayama, that it is an ACR gel. The gel is not easy to see even by SEM, by scanning electron microscope.
Yeah, it's really hard.
Yeah, I'm just worried. But when you do the micro, the hardness, were you using SEM? You were not, right?
Sorry.
When you did the micro hardness, what type of magnification did you use?
The micro hardness, for the loading we use 100 micronewton, and the magnification of it, and the magnification of the pointer is, I believe it was something between, I believe it was 100 micrometer or something close to that. I don't remember exactly the dimension of the diamond on it, but it's something close to that.
No, but I meant, Diego, when you magnify the sample itself.
Oh, okay.
Magnification, the view.
Yeah. I know, got it. The magnification of the microscope. You mean? Yeah, it was, I think, 40 times.
40?
Yes.
I think based on I did some work on ASR, on ACR, and I actually had some work that are not published for some reason, because anyways, but it's very hard to find magnification, but to find ASR gel, even when you go to 3000 magnification on SEM. So I'm just, maybe you need to have a look at it. Maybe that's not a gel.
Yeah.
The fact that you have silica, it might not be ASR gel. It might be silica within the aggregate itself.
Yeah, you're right. Yeah.
You might see something like a gel, but that could be brosside, because that's a secondary product of ACR.
Yeah, yeah, that's interesting. Yeah, yes, yeah. I'll look at again through it. Yes, you're right.
Because I see it here in your thesis that
Mhm.
of course your thesis did not focus on this.
Mhm.
A small part of your thesis that talk about ACR, but I think it's appropriate to put it in the right perspective and say, you know what, it needs more work or something.
Yes.
But I see the definition here, calcium to silica ratio of ACI reaction products.
Mhm.
So that
Oh,
term
yeah.
maybe need to
Yeah,
be.
yeah. You're right. Yes.
And then let me ask you another question about the oxide.
Mhm.
When we talk about alumina, silica, the calcium oxide in general, and I would tell you that I was in the same boat maybe 25 years ago, and we developed relationship between the oxide and the expansion.
Mhm.
But always there is a little bit of, we have to be very careful about the form of oxide.
Mhm.
For example, if you have silica, if that silica is in the form of quartz,
Yes.
it's crystalline, it doesn't contribute to the reaction.
Mhm.
If you have, quartz in the fly ash,
Yes. Yes.
and it's more important for alumina,
Mhm.
because most of aluminum fly ash is actually in the form of mullite or crystalline again. So it doesn't really contribute. So
Yeah.
maybe that's another. So I want to hear your opinion about that, and maybe you need to make that disclaimer in the thesis that really what is important is the form of oxide, not how much of it, whether
Yes.
it's amorphous or not.
Yes, you're totally right. There's one part of this final research in this thesis that because as you can see in the thesis, this final paper, it's not really like finished. We have, for example, for 38 the CPT test, we still don't have the 2 years of evaluation, and with the once we have all these results, we also will have the evaluation of the we would like to add in parallel with this ternary plot that give us not only like overall chemical composition of the main oxides, but also the reactivity of them together. For example, how much Portlandite consumption we will have once we mix the different SCMs together, and this kind of thing. So it's something that Leandro and we are thinking to add maybe a fourth information in this ternary plot to indicating the reactivity or the pozzolanic activity of the SCMs that should be together with cement to compose this the mixtures in this ternary plot.
That's very good, Diego. So with that, I also want to mention that to some extent, that the oxide tells good part of the story.
Yeah,
it's not like it doesn't mean anything. No, it tells you a very good part of the whole performance or story. It is just that little bit about the reactivity is something that you need to look into.
Yes, you're right.
Very good. Now with the self-healing of fly ash. So you have shown that the fly ash can actually, once there are cracks in the paste, the fly ash can actually heal up to 85% of these cracks.
The fly ash alone was able to heal 50% of the cracks. And it's very important to compare the results that we got by using fly ash and silica fume and compare them together. Because in one hand, we have a slowly reactive SCM, very slow. For example, for fly ash, we have like a slowly reactivity, pozzolanic activity, while using, for example, silica fume, it's much more reactive, and also it's the heterogeneous influence that this material causes in the hydration of the cement grains is also important. So as we can see, if we compare both results, we can clearly see that using silica fume, we have a reduction in the self-healing ability of the concrete. So this also is important because considering the reactivity of the pozzolanic activity of the SCMs, it's really and it's highly important to enhance the natural self-healing ability of the concrete. So this is why fly ash were able to increase natural self-healing while silica film decrease the natural self-healing, the ability to naturally self-heal the concrete.
So the silica fume, could you elaborate on that? The silica fume was not as effective as fly ash because of?
Because, let me share again the results here. It's going to be easier to explain. Just a second. So, for example, where is it? Here. So, as we can see, we have here just using cement. Once we crack the specimens at 28 days and after 90 days of healing, only using Portland cement with a quantity of 420 kg per cubic meter, we can see that only cement were able to heal 38% of the cracks in the cement paste. Adding 30%, not adding, but replacing 30% of the cement by fly ash class F, we were able to enhance this value to 50%. However, here, once we use 10% of fly ash, this number decreased in comparison with the control specimen. So the faster reactivity of the fly ash, and also the lower volume of silica film in the mixtures seems to decrease the ability to self-heal in the concrete.
I think I got it. So I think what you're saying is the silica film was consumed. It's
consumed before. Let's say it's consumed faster up to 28 days, and after 28 days, it seems that we have less unhydrated particles to contribute in the healing process.
Yeah, no, that makes sense. Yeah. But my question to you is, when you ran this test, you did the test with non-reactive aggregate.
Yes, exactly.
You have reactive aggregate. Reactive aggregate consume alkalinity, consume alkalis.
Yes.
My question is, will the fly ash, especially if it's low calcium, will the fly ash react at the low level of alkalinity left after the ASR occur? So there is a competition here between the fly ash and ASR.
Yes.
Let's say that the ASR goes faster or consume alkalis, and now you have the crack. You're expecting the fly ash to self-heal, fly ash to fill the cracks.
Yeah.
Actually, self-healing in that case, if it's a fly ash, it's a hydration product. So now that you have the alkalinity level drops, do you think that there is enough alkalis and calcium hydroxide to sustain the pozzolanic reaction of the fly ash?
Well, it's hard to say, but I think the battle between both, it's something that it would be a good idea to explore better with the samples that we have here, because it's very interesting in this case. We did not check like the influence of the ASR development on the ability of the fly ash to really heal, how it changed the ability of the fly ash to heal. So yeah, it's something that I think maybe better answer you, it would be better to try to explore more these results to try to understand better. Yeah.
Or maybe to add it to your thesis as a
yeah.
Something for future work. You don't have to answer all questions in your thesis. Sure. And then I have maybe one question, Mr. Chair. Do I still have time?
Yeah, no problem.
Okay. With the mechanical testing that you carried out, I could be wrong. I read your thesis more than 20 days ago, but I didn't see tensile strength, splitting tensile strength. You did not, right?
No, yeah, we did not do it. Yeah, the tensile strength.
Do you think the conclusion or the finding would be different?
In general, considering the findings in the literature, I think, for example, once we have the development of damage, internal damage, and the development of expansion in concrete, I believe the overall trend of the conclusions, it will be more or less the same thing. Of course, we will have something that could be something we could be explained better, or maybe could give us a little bit more like a variation in the results. But in general, I believe the trend of behavior of the specimens, for conclusion, it would be kind of similar if we would have tested the tensile strength as well. Yeah.
Very good. Thank you very much, Diego.
Thank you.
Okay, thank you very much. We will move on to Dr. Martin Perez then.
Thank you, Mr. Chair. Diego, I want to congratulate you for the amount of work that you have produced and your thesis. I really enjoy reading it. And I have to agree with Dr. Ideker and Dr. Shehata. You did an excellent presentation. And I must suggest that you actually tie everything together on the conclusion chapter. Because I read your thesis with these different topics being explored on each paper. But when I was listening to your presentation, everything kind of came together. So I think sometimes when you write a paper-based thesis, it tends to be a little bit fragmented, even though you have an overarching theme. It might be good before the conclusions for each chapter or each paper at the end to tie everything the way you did with your presentation, because you really did a very good job. So
thank you. Thank you.
This is just a suggestion for you and your supervisor. Obviously, you know that my background is not AAR, and I think all the good questions have been asked by the previous examiners. So I'm just going to try to clarify some of the things that perhaps I didn't understand as well, or I was curious as to why you did certain things. So one of the first, perhaps I'm going to follow up with Dr. Shehata when he asked you about testing the tensile strength. Because in a couple of places in the thesis, you talk about shear strength. And I can tell you, it's not really important right now where. I can give you my copy after. You reinforces. And I think you perhaps what you're referring there is more the state of shear stress than the strength, because the strength is a material property and it's independent of the applied loads. But I think what you're trying to say is that obviously when you have a state of shear stress, there is tension. So I was also surprised that that was not one of the properties that you tested. And again, I don't know if this is something that has been done for concretes that are subjected to alkali-silica reaction or not. But you did the compressive strength, the elastic modulus through this stiffness testing that you have. And I was wondering why not the tensile strength, since it's related to that shear strength that you're trying to quantify as well.
Well, one of the first, the option that we made for shear strength in this case, it's from one side, it's kind of easier to use this technique to test the concrete specimens, because normally once we test for tensile, there's such a variability in the tests, and also, for example, if we test for gas pressure for tensile, I don't even know if we have this type of equipment here at the university to test. So it was more an option to have like to be feasible to develop the test during the PhD, but also because both of them can give like such a great variability. So yeah, and then the option to not choose both together. It was also because to the delimitation of the specimens as well. So we need to choose one, and we choose shear because it was more practicable to develop in the lab with our equipments here at Ottawa.
Okay, I'll come back to mechanical properties in a moment. Another question I had, I know that you wanted to compare, so you wanted to keep the water to binder ratio constant, so you have a means of comparison different with all these mixtures that you have. But I'm just thinking, especially on the study where you are looking at surface treatments for existing structures, so structures that are in service. is that water binder ratio of 0.45 representative of everything that is out there? And is the water binder ratio a variable that would affect your results?
Well, regarding the surface treatment, yeah, you're right. It might affect, especially the adherence between the different surface treatment and with the concrete, but also how they will penetrate, like the different products will penetrate through the first layers of the concrete, because the water to binder ratio, it's closely linked with the microstructure, with the concrete. Once we have higher ratio, we have a lower quality of the microstructure with more cracks, more pores, which would indeed impact in our results as well. But in this case, we use the same water to binder ratio because we would like to keep constant the microstructure of the concrete to not have also this variability. But it's something that, of course, it needs to be checked for further publications or a better understanding of those charts, for example.
Yeah, the reason I'm asking, and again, I don't have the experience dealing with the structure suffering from AAR, but nowadays the standard specifies a lower water cement ratio or water binder ratio depending on of your mixture, especially when we have these stress mechanisms, right? That they depend on exposure environments, like water is an issue for AAR.
Mm-hmm.
And I'm thinking that when you are looking at the structures that have been in service for quite a while, usually you have concretes that have a higher
Yeah, you're right. Yes.
So more than anything, I was curious, why did you choose the 0.45?
We basically, the selection of 0.45, it's to be within the CSA variation between 0.42 and 0.45. In this case, we choose 45 due to have like to fix indeed the microstructure, but also because, for example, in the first part of this research, in which we use like different SEMs to have a good like fresh state behavior of the concrete, and then we keep the same water to binder ratio for the second analysis as well, the second part of this research. And then it was like, we just keep following the standard and keeping the same water to binder ratio. Yeah.
Okay. Good. Other question that comes to mind after reading your thesis, I found the studies about self-healing very interesting. Both the initial one without any induced expansion due to alkali-silica reaction, and then the ones that you have expansion due to ASR. And a question that comes to mind is, what happens when you have concrete that, in addition to suffering from this distress mechanism, is sustaining load?
Mm-hmm.
So how efficient is the ability of this and supplementary cementing materials in general, they tend to have a higher strength, so we know they are able to they have better performance for durability, but they also have a higher strength, so they are able to sustain load better as well. But I'm wondering the ability, this self-healing ability, how does it compare when you have a concrete that, in addition to what is undergoing in terms of ASR, is carrying load?
Mm-hmm. Well, in this case, I strongly believe that, for example, just first mentioning the first paper of the thesis, in which we caused internal cracking due to preload level, it was clear that the crack formation that we had in the cement paste, the opening of the crack were like thinner than once we have like, so in this case, I believe that once we have, for example, loading, depending of the element in the structure that we're talking about, of course, for example, if it's an element that it's under compression, for example, the opening of the cracks due to ASR might be thinner, and then it could enhance the behavior to heal, because the thinner the crack, there's a trend to enhance the healing ability of the concrete. However, for those that, for example, it's under tensile or a flexure condition that we have tensile in the bottom part of the beams, we might have a wider cracks formed on it. So in those cases, I believe that then the self-healing ability will decrease due to the opening of the crack that it's wider. So it really depends of the element in the structure. Yeah.
Okay. Thank you for that response, but I'm also thinking about sustained load. So your samples, what you did was you preload them and induce a certain mechanical damage, and then you kind of put and the damage is done and is kind of dormant, if you wish, because you don't have any other mechanism that is either closing those cracks in addition to, beyond the self-healing, or opening the cracks because there is more load. So I'm wondering when they are sustaining load. So you have, even if you are at 40%, I noticed that you said 40% and 0%, you have the same performance. And I think you would have expected that because you assume that the concrete is within the elastic range around that region. But what happens if you sustain at 40%, I don't know, 20 years?
Yeah, then, for example, if we have the sustained load like that, we might have a crack development at some point. And then I think it would be a battle between the crystalline admixtures and the development of crack due to the sustained load. For example, if it's a higher load in the concrete in which we'll have a faster development of crack, then it might the constant load will develop more cracks more faster than the ability of the concrete to self-heal. So first, it depends of the percentage of the load, but once we have, for example, 40, I would say that at some point, 20 years, we will have development of some cracks, and then I strongly believe that at this loading level, at least the crystalline admixtures will able to heal some of the cracks, but it's interesting, of course, to check if ability to self-heal will increase or decrease over time due to the constant load in the specimens.
Yeah, and I think it would be interesting, and of course, I agree with Dr. Shehata. You are not supposed to answer all the questions because otherwise you put out of work the rest of your colleagues that are doing the master PhDs. But it would be interesting to see also what is the interaction, for instance, the relaxation due to creep, right? Because that's an issue that happens over time. So that was something that came to mind. I have a few questions. Perhaps if I direct you, I don't know if you can open the thesis and I direct you to certain graphs that I had a little bit of a problem understanding, and perhaps I missed the details while I was reading. One of them, if you go to page 88, I don't know if you can open the thesis.
Yes. It's page 88 of the
I believe actually it's page on the PDF is 110.
All right. Yes.
So I'm looking at the. So let's look, for instance, at 6.9b, and then you have at 0 date. So basically, at the 0 line of that graph. How did you calculate the variation there? I didn't understand when you're talking about compressive variation at 0 days.
Yeah. Here, first, it's not exactly at 0. We preload the specimens, for example, at 28 days, and then we test for compressive, for all tests that we made, it was 3 days after the preloading, because we would like to have some recover of the concrete after the preloading. And this variation here, it's calculated based on the specimens that we did not apply any preloading level on it. So it's basically the difference between those that we test without preloading with those with preloading levels.
Okay, so maybe you want to clarify that in the text, because I didn't understand, and I kind of scratch my head a little bit trying to understand how you got those values.
All right.
Now, if you go to pages 112 in the PDF, and at the end of the page, you're basically saying that the higher the preload level, the higher the damage in the concrete, and you're defining the damage as various types of deterioration mechanisms, and you include loading there. Would you consider loading a deterioration mechanism?
Loading in general, like no, but like in this case that we applied a load specifically to damage the concrete, like at levels that we would have the development of cracks in the concrete, we consider like in general because of that, because we load the specimens to levels that we due to the load application, we would have a crack formation in the cement paste or in the aggregates at some point as well.
Yeah, I think I understand what you're trying to say, but perhaps I'm a little bit coming from a hybrid between structures and materials. I have to put my 2 cents here. When you're showing you talk about harmful consequences of various types of deterioration mechanisms, and you include loading.
Yeah.
I mean, we design concrete structures to take loads, right? So that's what they are designed for. So the way I understand deterioration more is a mechanism that takes over time, and it's something that is not really intended. It's not, I mean, we design to prevent or to mitigate, like in your thesis, you are trying to enhance the design process. So you minimize the effects of these mechanisms. I will include loading as deterioration mechanism, right? And I think what you're trying to say is that there's an damage. Damage can happen either from loading or from just make reference of what we already know, that concrete we assume to behave on the elastic range around that range of load in terms of the compressive strength. Okay, page 99, I have to figure page 99, I think it's 120 in the PDF. I should have written it in terms of.
Yeah, it's 121.
121. Yeah, so I found this interesting, and I was thinking about when you're talking about the crystalline admixture, fully healed, around 80%. After 9 days of self-healing curing, and then you say at 180 days it was less efficient.
Yes.
So you argue that it loses its ability to self-heal. But I saw some graphs, and I don't know if they are on the on the next page. And if I look at your the number of cracks that through this DRI analysis, the damage rating index analysis that you perform, I observed that there is more damage at the samples that were at 28 days.
Yes.
So I'm not arguing that is not less.
But also, for example, SCMs here, because up to 28 days, it seems that we, for example, comparing the compressive strength between 28 days and 180 days, there's at least a difference in between like 10 MPa to 50 MPa. So it seems that the microstructure is not well formed at 28 days yet. I know that we use this 28 days as the strength for structures, etc. But considering this difference, it seems that we still don't have a very good microstructure in the specimen. So once we preloaded, it were able to form a little bit more cracks. Yes, you're right about that. But then it's also correlated with the let's say the amount of unhydrated particles from the SCMs or from the cement, because the crystalline admixtures works closely with those particles. So at for example 6 months, at 180 days, there's a trend that we will have less unhydrated cracks. So this could this is directly correlated with the fact that we have a decrease in the self-healing ability of the concrete, even if we are using crystalline admixtures.
Okay.
So yeah, you're right, but also there's this explanation. Yeah.
Yeah, no, I don't argue against what you explained in the thesis. I was just considering if you had also to do that, you had less damage to begin with at 180 days, obviously for the reasons that you just explained, but that might be reflected on your quantification at the end, saying that it loses its ability to start healing.
Yeah, also there was a trend with this analysis that once we preload the specimens at 180 days, we found that for especially once we used, for example, fly ash, we got like a higher amount of cracks in the aggregates after preloading the specimens, because we checked that the compressive strength of the concrete in which we used fly ash, it was around 60 MPa after 6 months. So we had a higher amount of cracks in the aggregates and a little bit less amount of cracks in the cement paste.
Which is characteristic of higher strength concrete. Okay, Mr. Chair, I can let you go for the second round.
Oh. Okay, great.
Thank
so
you.
we'll move to the second round now, and we'll go back to our first external examiner, Dr. Ideke. But other people can jump in as needed. Other examiners can jump in as needed at any point during this.
Okay, so I just have maybe a bit of a follow-up question from my previous one about the framework that you recommended and looking at the oxide analysis. And I definitely think the oxide analysis for the SCMs is important, but just thinking more broadly, what to include if you had the ability to pull those into a framework? So again, I'm not suggesting it's work you should have done, but let's say you could pick out any sort of information that you wanted to have to strengthen that framework. What would it be, and what would you?
Well, the first one for sure, it would be the reactivity of the materials that we are using. Like if you're using fly ash, we have like a different reactivity than metakaolin, for example, or silica fume. So indeed, for the first choice, it will be, and it will be, the addition of the information of the reactivity of the and looking to them as a function that is related with that's the end. And then, yeah.
Okay, so maybe if this is sort of along those same lines, I ask you to take a step back and try to remove yourself from what we say as being in the weeds, right? I mean, you're finishing this up. You're very much in the weeds, if possible, and take a look at that framework, the way it's developed now, and the way you've got that, the figure sort of proposed now. What are the limitations of that? What's limiting how broadly applied or how generalized that might be?
Well, first, it would be for sure important to have first more points to describe better those zones for each of the different risks of ASR development. For sure, it would be interesting to have like middle points between those that we selected in this research. Also, it would be interesting to test those mixtures for different reactive aggregates, and also in conditions like in the field conditions, like using blocks, for example, because if we expose for different scenarios, like different weather, like drying and wetting cycles, or freezing thawing cycles as well. This is important for the development of damage in it. But I would say that this is just the first draw of it, but it still needs like lots of development to really apply them for field concrete and etc.
Yeah, that's good. I sort of asked you the question a bit of a different way to see if you bring up the aggregate side. I think that's something that, again, it's not a criticism. I think you did a lot of excellent work and really looked in depth, but focused on very highly reactive or extremely highly reactive aggregates. And I think extending that out, you might get some really interesting results too, right? With more lower reactivity type aggregates. And I think that's needed to generalize that approach. And I think maybe just one thing, I hopefully you've seen the review comments that we all, were able to put in. I think one thing that's maybe missing from the end of your thesis, and Dr. Martin Perez, I think, highlighted this really well, is sort of tying it all together. And I think part of that is a future work section. Because, for people that are continuing on, either from your advisors research group or from other research groups, I think it's really important to also, you're not trying to give them the answers, but give them a bit of a roadmap to say, here were some of the limitations in my work, and here's where you can build off of. And it's not to give them a short hit list so they don't read the dissertation, right? But they need to hear it in your words. And I think they need to understand from you, since you're the expert in this area now, what the things are that you would do to sort of build. And I think that could be one of the pieces that also helps to tie together that sort of paper-based thesis.
Add that to the university, and yes, you both are completely right on it. Yes.
And I think it's one of the really interesting things about the AAR community that is a bit different from other types of durability issues. I see this community as being actually quite well linked together. I mean, you had a number of people from across the globe at your defense today. And I think that that's a real plus. I think it's a real positive thing about being in the AAR area, that we tend to exchange a lot of information. We tend to build off of what each other do, and we try to not necessarily repeat things. Of course, we always do that anyway. That's just the nature of research. But I think we're trying to do less and less of the repeat and more of the sort of building side of things. That's an important takeaway. But just a comment. So I'll pass it along to others who want to jump in at this point. That wraps up the question.
Dr. Shahada, do you want to add some questions in the second round?
Sure, just a couple of questions, Diego. So the admixture itself, the crystalline admixtures that you used 4 of them, right?
Yes.
Is there? I don't recall seeing something in the thesis, but maybe I missed it, that differentiate between them. Maybe the chemical composition is something that you cannot share. Maybe the company wouldn't allow it, but at least how they work or the main difference between them. Do we know anything? Do we know?
Yes. Basically, the difference among them, they are like in the chemical composition, the general chemical composition of them. There are some that we have like more silica or more aluminum on it. Also, more or less magnesium on it. So they vary in this type of ways. Like the chemical composition of them, generally it's variable, but it's something that we cannot add in the papers, as you said, because it's like it's an information that from the industry that we cannot share. Yes.
Is there one of them that relies only on the formation of calcium carbonate?
No, that it's focused for that. I don't think there one that it's for that, to form calcium carbonate. But there's a trend to have some calcium carbonate formation in the healing products, in the cracks, indeed. Yeah.
Yeah. So in that case, Diego, if it is a form of alumina silica, so is it fair or is it accurate enough to say that they do self-healing similar to a fly ash or any supplementary cementing materials?
I would say in parts, at least like those crystalline admixtures, they trained to form more CSAs together with the SCMs and the unhydrated cement particles. But I would say at least they are a little bit different. If we would say like, oh, just the self-healing sink for SCMs, I would say they are a little bit different, not exactly the same, due to the fact that we have a higher amount of carbon in the products, as you said, but also a higher amount of magnesium, etc. So it's a little bit different, not exactly the same product as the hydration of the SCMs or the cement.
You know what I'm thinking, and of course you wouldn't be able to answer, Diego. We need the chemical composition. Is there is a competition here, because if you want to turn the calcium hydroxide to carbonate, And in the same material, you need the calcium hydroxide for the pozzolanic reaction.
Exactly.
So really, it's and then how much do we have left after the ASR formation? So I think it's, I mean, for the very future, for your postdoc or for your work as a professor later, we need to look into this. This really a piece all the scientific community will be interesting to look at.
Yes,
definitely. Your paper or your thesis. So I'm gonna have two questions, very short.
All right.
First one about the hardness, micro hardness of gel. So some of them has high hardness, some of them high low hardness.
Yes.
Question one, which one is better? Question two, is there a relationship between hardness and viscosity?
Yes. In general, the surface hardness of them, I would say that the better one, the best gel, considering the surface hardness, are those that we have a lower surface hardness of the gel. Why? Because normally, once we decrease the surface hardness, this is linked with the amount of calcium in the gel, which means that the viscosity it's decreased as well. So I would say that it's better to have a gel with a lower surface hardness.
Very good. That's a very good answer. Thank you.
Thank you.
My very last question.
All right.
If I tell you have a new mix and you're planning to put 25% low calcium fly ash, works with most. If you are the end user, would you go with a 25 plus crystalline admixtures, or would you go with a 35 fly ash and close the story?
Yeah, this is hard due to the fact that you asked before about the amount of calcium, but definitely, like at least for field, it would be good to first try to avoid as you can the development of ASR, and then try to use a backup such as crystalline admixtures. If we have them the condition of ASR development, this could help in the future. So it's hard to say exactly due to those facts that you said before, due to calcium. But in my opinion, I would opt to have 35% of fly ash and using the crystalline admixtures.
Okay. How about 50% fly ash?
Yes, then I don't know, because we will have like such the material will change that much. Then I don't even know if we would have like a complete hydration of the fly ash in this condition. So I think it depends of a lot of variables. That we should how reactive is the fly ash, the chemical composition of the fly ash. I think it's in that case, then I don't think it's the best option to select 50% of fly ash and combination with crystalline admixtures. It depends, I would say. The answer. Yeah.
Thank you very much, Diego.
Thank you. Yeah.
Thank you, Mr. Chair. I'm done.
Okay. And at second round, Martin, Dr. Martin Perez.
Thank you, Mr. Chairman. I just have one final question regarding figure 923. It's on page 246 on the PDF.
All right.
So I want you to explain me this figure, because I had a little bit of difficulty understanding, because I don't understand how do you get the initial performance loss.
Oh, the initial performance loss we got. Well, the performance loss, as I mentioned, it's the average of the mechanical properties that we test. So in this case, it's a comparison between the damage control specimens with sound concrete. The same mixtures that we left them at 12 degrees Celsius to not develop ASR. So it's the comparison between the damaged concrete with those that with the sound concrete. So it's basically that, and it's the performance loss of the concrete before applying the products on the surface. So it's always comparing with sound concrete. Yeah.
Okay, so the controlled mixture here, I went back to the table and you say it has any coating material.
Yeah.
Do you mean that it has a coating or it does not have a coating?
The control specimen does not have coating. We treat the surface similarly to those that we apply different products to not have the difference, like that variability as well. Because, for example, we had to treat the surface to have a better adherence for the different materials that we used. So I did the same for the control specimens, but then I did not apply anything on the surface. So it's just to have the same situation, let's say, and the same type of concrete for all mixtures, but there is no application of any product in the control specimens.
Okay, so you might want to correct, and I think it's table in page 196. So let me just tell you exactly. So yeah, it would be 220 in the PDF, maybe. No, so it is 218 on the PDF. Oh, no, 219. So table 9.4.
Yes.
I think this is why I got confused, because you say control and it says coating material any.
Yeah.
You mean none?
Yeah, exactly.
Okay. Yeah, because I was not clear what the control represented, so therefore I didn't understand what happened to that mixture.
All right.
I think that's it for me. I just have one comment that I put on my report. I think you did a good job separating the different themes into these papers, but you have these odd chapters, chapter 3 and 5. In my opinion, I think they're a little bit hanging in there. Perhaps you can just consolidate them on chapter 1 and you really talk about the research objectives on chapter 1. Maybe if you want to do a summary of the state of the art and what are the gaps at the end of your literature review chapter, but the research objectives should be in chapter 1, as well as the organization and how you have formatted the thesis. Because I found at times, you go through the literature review and then you have this 2-page chapter that is basically telling me what is coming up. And then chapter 4 is really your experimental methods, right?
Yes.
I might call it experimental methods because I found the title was not very representative of what you had in there, although I understood what you had in mind. And then chapter 5 is another chapter that you're saying, okay, now is the important thing is starting now, right?
Yes.
I would move that to chapter 1 to consolidate everything in that chapter. I think the flow, in my opinion, the flow of the thesis would be better. I know that, when you have paper-based thesis, there is a little bit of redundancy and repetition. It's difficult to overcome that, but if you have, you start with your research objectives and how you are using the methodology, present your work on these papers, and then at the end, on the conclusions, you tie everything. The thesis will have a flow and it would, everything will come together.
All right.
Better,
Okay. Thank you.
Thank you, Diego.
Thank you.
Okay, we're going to give Dr. Sanchez a chance to chime in.
Okay. So first of all, I would like to thank the examiners. I know very well how much time does it take to go through a thesis and a super, I would say, extensive amount of work that Diego has done. So thank you very much for your time, contributions. I guess I took notes on all of the comments, and we'll make sure Diego addresses everything in the end. I think the comments were great. I'm not gonna ask questions to Diego as I normally do to all of my students, because it's been almost 5 years of questions every day. So at some point is enough. But I do have a couple of comments here, and I would like just to, after the comments, to address some comments from the examiners as well. First of all, Diego, I'd like to congratulate you quite a lot.
Thank you.
It's been really a pleasure to work with you over the past 5 years. I still remember the day I was one of your examiners of master, and you impressed me with your quality and so on. And then you expressed the desire of becoming a professor and researcher. And I was already sure by the time that you will be doing a great job. And now to see everything materialized this way, it's a great honor and pleasure to have had the opportunity to work with you. So congratulations. I think you did great. This is a very challenging topic. I mean, everybody knows that ASR is extremely harmful. Medhat, Jason, myself, and even now Beatriz, we brought you to this as well right now. So we are having fun working with ASR. The problem is that nobody knows how to stop it. And Diego, put his shoes to try to at least help us in this regard. There is a new committee, RILAM, tackling a little bit more alternative products where I have the pleasure to work with Medhat on that. And one of the products could be the use of self-healing. And then Diego tackled that in a fashion that tried to see if that might work or not. And he did, I would say, a phenomenal amount of work in terms of quality, but also quantity, right? Normally, students are not necessarily happy whenever we increase their testing matrix. I have some of them that sometimes say, oh, Prof, probably is too much. But Diego was kind of a student that always was even more, I would say, happy to do a little bit more and to achieve a little bit further. And it's so nice to work with a person like this that it gets you even more excited and motivated as a professor to keep pushing things. Diego has been very humble, to be honest, with all of you in this presentation, because he just showed 50% at the most, all of the works he has done over the past 5 years. So we also worked with different aggregates, but we didn't have space to present even written space or space here in the presentation and so on. But I mentioned to Diego that in his postdoc and future career, he has at least 5 to 10 years of time to keep just publishing everything he has done already. So this has been just, to me, incredible. Now, I just would like to address a couple of comments here. First of all, Jason made a super nice comment on statistics. And for those that don't know, but probably just a few, but Jason is the chair of the other RILAM committee in which statistics has been addressed quite a lot, or is going to be addressed quite a lot in terms of the evaluation of performance in the field. And I've been discussing that with Diego about Tukey test, ANOVA, and so on, because I think definitely one of the things that misses quite a lot in our field, ASR, is statistical evaluation. So sometimes we classify performance as per that little value, 0.04, 0.12, but we don't compare from one another with a more statistical approach. And I think Diego did a great job, and hopefully this is going to be usable, I would say, for some task groups of Jason's committee. Now, Beatriz and Medhat, they asked questions on the shear test. That's very interesting because I bring this, I would say, for a couple of years. So the direct tension, that probably is the best one. We try to do that, but we often have failure at the glue. So we can't really measure deterioration. Then we did the splitting tension test. And being a Brazilian, and because that's called a Brazilian test, I think I can say that is a bad test. So, and why it's a bad test? Because there is so much variability, especially for deteriorated concrete. For sound concrete is slightly better. I understand all of the structural engineers that use that for a more structural perspective, but regarding deterioration, it's very variable. So then we've done, I've done in my PhD gas pressure tension at McGill. And that was really good, but the problem is that it was diagnostic up until a given point only. Above and beyond 0.10, we couldn't see differences in deterioration. So then we decided, Diego and I, to develop. It was not a development, the test setup itself, it was more an adaptation, right, yes, Diego, to ASR, something that already existed, and the results were great in terms of being diagnostic. And why we decided to do that? Because ASR cracks are mainly in the aggregates at the beginning. So I thought that the aggregate interlock might have been reduced, and probably with a very simple setup, we could measure that. And this was exactly the case. So it's a very simple setup. Since there are lots of cracks in the aggregates, you have no longer aggregate interlock, the crack goes through and splits the aggregate, and then you have failure. It's still a little bit more variable than the SDT, but it's less variable than a tension test. So we are kind of trying to push forward. We got a first publication on this, but now we need to do other mechanisms as well, and other aggregates and so on. So that's a little bit the explanation on this test. Then Beatriz, you asked such a nice question on application to structures, and I think I echo what you said, and with Jason as well. I've had the opportunity to discuss with Jason before, and sometimes we do lots of performance tests in the lab, but the results are good to evaluate, for example, if an aggregate is reactive or not, but it's not able at all to evaluate if that concrete is going to be good for that structure. So I have a feeling that materials engineers, they don't work with structural engineers that much, and there is a really gray zone between the assessment of the material in the lab and the application. That's why, by the way, Beatriz, that I'm very glad to work with you and other colleagues in our department here to try to decrease that gap a little bit that exists. And some of the, for example, the water to binder ratio you mentioned, I agree with you. The problem is that is standardized. If you don't do that, you cannot evaluate performance of the aggregate. Now, with that being said, evaluating the performance of the aggregate. Now, can you reevaluate the performance of the structure? Probably not, because it's not allowed as per CSA. So how can we minimize that discrepancy, if I wish, between materials assessment and structural performance? I think this is a huge gray area that we as materials or structural engineers, we need to try to push and get guys to work together to try to limitate a little bit that. Another comment I would like to make is that I really like it, the way, Jason, you try to push Diego. Diego has lots within him to let the answers to flow, and I discussed with him on using aggregates with lower reactivity. He did. He didn't report all the things because of time, but we indeed use it. Sudbury, right? Sprat,
yeah,
and the alkali carbonate reaction. So I think we would. So this Sprat has already a lower reactivity than the Spring Hill, and Sudbury even lower. So I think we are from moderate to super high reactivity. We will have an idea, but I agree with you. This is just the first, approach in this regard. We will need much more than this. Especially regarding the release of aggregate, the alkalis from the aggregates as well. That's something that that theory plot needs to account for at some point as well, right? We are normally used to say that alkalis come from the binders, but I mean from the aggregates might be an important contribution. And my last comment, I promise, is about the 50% that Shehata mentioned, Medhat. I remember we all know Benoit Fournier, and I remember Benoit before I started my PhD with him. He said, "You know what, Leandro? Moan Malhotra one day told me something. Let's put 70% fly ash, and there is no more ASR in the world. And why you guys are still studying ASR, right?" And that's kind of true. I agree with that. The only problem, and as you know more than me, with such a high amount of fly ash and so on, we can have potential other issues as well, scaling and others that, in Canada, we need to account for those things as well. But I agree 100% with you. And I like it, your answer, Diego. We need to go for the maximum, because I think every single project, like Diego's project, we realize that we need to prevent ASR. Once we have that problem, we have a huge societal issue, I would say. And putting the SCMs, the higher the amount, the better. And then why not using other alternative products such as self-healing for a backup, right? To do that even better, to increase that even more the service life. So again, thank you all of the examiners. Congratulations, Diego. I think you did not only a good, but an exceptional work. And that's all for me. Thank you.
Okay. So at this point, we are going to go to the time when we start deliberating. So I'm going to automatically send the people who are in the audience here out physically, and the people who are remotely, I will ask them to leave too, and of course the candidate. And so that should, open all rooms. I'll just wait for everybody to sit down. So I am pleased to announce, Dr. De Souza, that you have passed your defense and you can henceforth call yourself Dr. De Souza. You have to submit your final thesis with some minor changes. I'm assured that you probably will be able to do those in just a few days by your supervisor. And congratulations also to the supervisor. And thank you very much to the examiners, the two external examiners, and Dr. Martin Perez for your participation today. And everybody can now congratulate. And good. All right. Okay. Excellent. So that if I would be fine if people who are online also, you can open up your audio and say congratulations too if you want as well, and your video for that matter if you want. So I'll leave it up to you. We can all have a little celebration here, and
congratulations, Diego.
Probably, you know, that one's okay, but we still have COVID, so
Probably we could give him the chance to say something.
yes, go ahead, say something. Yes.
Yes. To say something, can I just open another presentation, because I would.
By all means, if you like. Yes,
Yeah.
sure.
It's gonna be fast.
Sure.
Just let me first. Just let me share it, and then. Well, I'm not really good for like good words like that at the end of something, but. I would like to show some pictures and try to explain some of my feelings. Oh, it's here. So first, Leandro, I have the picture from the time that you were there in my master defense. At that day, I remember that we talked after the defense, and you invited me to come to Canada. We met after that to confirm that if I would be coming or not. But for me, I was like sure already since that day. It was a pleasure for me, and it's such a nice thing because 3 years later, you were there in Curitiba again, and we met again with our family. You were there. It was such a great thing because, as I always mention, you are like family for me. You are like my second father. So it's not just because of the research, but all the words that you are always like saying to me for my life, how to be a better person and how to achieve my goals in my life. So thank you. Thanks a lot because of that and all your experience, everything. Thank you, Leandro. But I also would like to add my pictures from my family here, because after that moment in 2016, I have to let like my family back, and it's hard to live far from them because, well, I love them so much, and it's pretty hard to live far from them, especially in moments that you feel alone. But one thing that was nice to come to here, these are the first pictures we take here in Canada, like the first week that we were here, the first picture, we stayed in a jail in the first hostel. Our first like apartment, so it was so small, so small. Our furniture, and then the weather here is such a great thing in comparison with Brazil. But I feel that I was in a family here. I met such a great person here, and the group, they were always with their open arms, and I feel really, really part of it, like a family. And during all this process, I have an opportunity to meet the graveyard of blocks from Benoit. It's interesting here that M.Sc was there, as we can see here. So we start together, and now we are finishing together. It's such a great thing. So and we won some awards together. We celebrate together. Your first block in the lab, we were there together. We were there. Lots of different conferences together. Benoit here again with you guys. It was such a great thing. Luan here as well. International conference as well as here in Madrid with Esperanza here. So it was so great. We worked hard, very hard in the lab. It was like 4 years of very hard working in the lab, especially with this guy here that I lost, that we were like together basically almost 24/7 at some point, like working together every day, every time. And you are my family here in Canada. I know that I left my blood family in Brazil, but here you are my family, and I feel like, yes, I choose this family, and I really feel part of something. Also, we don't we don't support the same teams, but besides that, it's great to have some games to make fun of each other. It's fun. I would like to thank my wife, because without you, this would be impossible, completely impossible. Our family, it's every day bigger. Our crazy cat, sometimes like when I like need something, he's there just sleeping. And then when we start like meeting at Zoom, he starts to be crazy, like because cats are like that. And of course, this is a sad moment here, because my nephew unfortunately died this year, and it's hard for me to say that, because he did not like unfortunately COVID he passed away due to COVID. So, and it was during this year. So unfortunately, I cannot say that this is the happiest year of my life, because my beloved nephew unfortunately left us. And I would like to dedicate this title and all this presentation to him. I know that wherever he is with me and giving me the strength that I need to defend my thesis and to hold my title. Thank you. Thank you, Nildo, for everything. And at the end of this presentation, thank you, my family in Brazil, and my family here in Canada. And once again, thank you, Leandro, because you inspire us a lot. And every day, as I told you, like 4 years ago, I would like to become a prof. And now that I passed 4 years with you, I'm sure that I want to be a prof, because you are that inspiration for all of us. Thank you. So, okay.
Well, congratulations.
Thank you.
Congratulations.
And thank you for the committee as well. Thank you, Shihata. Thank you, Beatrice, and thank you, Idakar, as well. Thank you for your comments and for everything, for your questions. Thank you.
Congratulations, Diego.
Thank you.
And all the best to you, Diego. I'm sure you will all be proud of you very soon.
Thank you.
Hey, Diego!
So
I'm going to send you the thing. I found it.
no. It's on the printed scan board. Just confirm the content.
Obrigado, Marcelo.
Fantastic.
Abraço para você, abraço para toda a minha família que está me acompanhando aí, para todo o pessoal lá da UFR. Para você. Valeu, Leandro. M.Sc, where are you?
Not M.Sc anymore. Doctors are
It's been a great work with you. Thanks a lot. You haven't had a chance to. It means, yeah, it means a lot.
It's like me to keep this open, right?
Sorry?
You want me to keep the video open?
I don't know if they stay there, but
I'll let you decide with the room. I
Yeah.
can close it now, or if you want to, I can stay.
Can I
Keep it open.
Sure. We still have a good half hour.
As you can see, it's always the wife that decides. I know that very well.
Numa breve viagem no tempo, encontramos os inconformados, os estudiosos, os precursores, os incansáveis, os carregadores de piano, os cientistas, aqueles que buscam encontrar as origens dos problemas construtivos, as causas das manifestações patológicas, preveem o prognóstico, especificam as terapias, projetam os reforços, analisam os acidentes, aprendem com eles, implementam critérios normativos e aprimoram a qualidade em prol da durabilidade e da sustentabilidade das construções. Você pode apelidá-los de raiz, cringe, baby boomers, geração X, mas prefiro chamá-los de sábios patologistas das construções.